Bom, muito obrigado pela paciência de vocês. Houve um problema de a rede do IMPA ter caído, parte deles. E nós esperamos, porque houve o compromisso de transmitir a palestra do professor Michael Atiyah para 26 outros pontos no Brasil, além da internet. Então, acho que valeu a pena, de todo modo, esperar essa conferência de um dos grandes matemáticos do nosso tempo. A contribuição do professor Atiyah na matemática vai de topologia algébrica, álgebra, e coroa-se certamente com o teorema do índice de Atiyah Singer, que influenciou fundamentalmente a física teórica, pelo menos parte dela, através de brilhantes alunos que ele teve e de brilhantes matemáticos que seguiram essa roda. Então, é uma honra, uma satisfação apresentar o Sir Michael Atiyah.
So thank you very much for this invitation to visit not only Rio, but 26 other places in Brazil all at the same time. And it's a great pleasure to be back in IMPA. The topic I'm going to talk about is solitons. But before I start on the topic, let me give you some general background, philosophical background. Now, mathematics starts really with linear mathematics, the most elementary kind of mathematics, and it goes back historically to Euclidean geometry, straight lines in the plane, angles. Then we do linear algebra, matrices, eigenvalues, and then you do linear algebra over infinite dimensional spaces, in other words, linear analysis, and including this, things like Fourier series, spectral theory, with applications to quantum mechanics. This is all linear mathematics. It's fantastically successful. One of the great achievements of mathematics was the development of very sophisticated treatment of linear problems. Then, of course, the world is not linear, so going beyond linear problems, you can first study small-scale perturbations about linear problems. In the geometrical form, this might study situations where space is not flat, but curved with some small curvature. Or if you do it algebraically, you expand in power series and you throw away terms after the first few terms, if they're small, by approximation. So this is the traditional way of going from linear to nearly linear, by small perturbations. But then there are much harder problems, which are non-linear mathematics in global scale, which you cannot attack by traditional linear methods or approximately linear methods. Again, if you start in finite dimensions, algebraic geometry, studying solutions of polynomial equations, these are finite many degrees of freedom. This is a good example of non-linear finite dimensional mathematics. Topology, which goes along with that, is an interesting global phenomenon which you can study in finite dimensions. And then you can try to apply this also in nonlinear differential equations, ordinary differential equations, partial differential equations. Here, of course, you're dealing with infinite dimensional spaces, function spaces, so the topology of function spaces comes in. So this is a kind of broad scenario of background to what I want to talk about. Now, solitons can be defined in a very broad way as solitary wave solutions of certain special kind of nonlinear partial differential equations which behave like particles. This is a very crude description, not very precise, but it's good enough. And these equations are special, but they include very many important special cases. The history of this goes back into the early 19th century, but only really began to be developed in an important way in 1965. After that time, there was what you would call explosive development. Large number of activities developed. Now, the theory begins, the first part is what I call the one-dimensional theory, or really 1 plus 1. One dimension meaning space, one dimension meaning time, studying functions of one variable which evolve in time. There is a beautiful mathematical theory which is related to Lie groups, scattering theory, integrable Hamiltonian systems, all of which is used, and this produces general methods for constructing all the solutions of this class of nonlinear differential equations. These have important applications and origins in the study of water waves in the canal, pulses in optic fibers, many other examples which have important applications in physics and engineering. So solitons are of great interest in the practical world, but also they have a very beautiful mathematical theory. But I want to talk not about this part, which is very well understood, but I want to talk about higher dimensions. Dimensions 3 and 4, that depends whether you include time or not, so 3 or 4. And these examples really come from particle physics. These problems are much more complicated, and there is an elegant theory in some very special cases. And these particular cases, which are special, you can reduce those down to lower dimensions by concentrating on solutions that don't depend on some of the variables. If you have a function of 4 variables which is independent of 2 variables, it becomes a function essentially of 2 variables. In this way, you can reduce a problem from higher dimensions to lower dimensions, and if you take these problems in 4 dimensions and reduce them in different ways, you get many examples of integer systems which are in 1 dimension. The theory I talked about before can be seen as coming from one theory in higher dimensions. These equations can be solved. There are very special ones, but they can maybe give a guidance to some other problems which you cannot solve in exactly the same way, and I'll talk about that later. And one of the important things to come out, and this was realized by physicists, is the key role of topological ideas in this story as a strong guide to help you understand these difficult problems. Now, that's by the way of general introduction. Let me go back, be more precise about the one-dimensional theory. The first equation that was studied is the so-called KdV equation, the Korteweg-de Vries equation, which governs the motion of water in a canal, where the function u represents the height of the water, x is the distance along the canal, and t is time. And so you study the evolution of water in the canal, and the approximate equation that describes these under suitable conditions for the size of the canal and the size of the wave is this differential equation here, the Korteweg-de Vries equation. These represent partial derivatives, so this is partial derivative with respect to time, u sub x is partial derivative with respect to x, this is 3 derivatives. And the important thing to notice is that there's one term in the middle which is not linear, it's the product of u times the derivative. And the solutions to this equation are the ones that show the soliton behavior. And what happens is that, well, first of all, you must decide to solve this differential equation with boundary conditions, and you assume that this height u goes to a constant height, say 0, at infinity in both directions. X goes to plus or minus infinity. And the soliton solution is actually an explicit function. You can write it down. A single soliton is a function u of x and t that depends only on the difference of x minus ct, where c is a constant, that a single function of one variable. This single function of one variable is given by this simple formula involving the hyperbolic secant squared. And you plot the graph of this function, it looks like this. It has a bump. And because it's the form x minus ct, as you propagate in time, all that happens is it's a wave that travels with velocity c. So this is what it looks like at time 0. Later on, it's the same thing this way, or backwards in time, it's the same thing that way. So this is the traveling wave, which actually you can see if you go out on the right day in the water, you're lucky, you'll see a traveling wave moving down the canal. This is a very special solution of this differential equation. But it turns out, and this was discovered much later, that the general solution for any initial condition of bumps and so on, you find eventually that if you wait long enough, then eventually you'll find a certain number of bumps appearing. And this finite number of bumps might in general be n, and you'll get some velocities, c1, c2 up to cn, each bump traveling with its own velocity, each bump looking very much like this function here. We notice this bump function has two parameters, c here and c, so this one of them determines the speed, the other determines the height, the bigger one travels faster. And moreover, if you go backwards in time, then you find the same solutions emerging in negative time, but in a different order. I'll draw you a picture. And this was all discovered for the first time on a computer. And it's because of the availability of computers to examine the behavior of complicated equations that some things have been found out. And this subject really could not have been developed before the computer came along to make the calculations possible. So that was why it had to wait until the middle of the 20th century before it developed. Now here is a picture, just to show you a simple-minded picture, for n equal to 2. N equal to 2, I've drawn this is what you imagine the water looks like at a certain time in the past, and then you let it propagate according to the equations. What happens is this one is traveling faster than this one, so at some time they interact. Something complicated happens, but afterwards, after further long time, the big one reappears in exactly the same looking shape as before, and the small one is left behind, and exactly the same as if this one had just passed through with no interaction. The only difference is that there's what's called a phase shift. That is to say, the relative distance between these two is not exactly what you would think if they'd been freely non-interacting. They shift by a constant. But except for that, they preserve their identity. So that's why these things are like particles. They can interact, like bouncing off each other, but eventually they emerge with their own shape back. And this is what kind of fact was discovered experimentally, and is the beginning of the theory. And it's a very remarkable fact. Great surprise to those who studied it. Now, there is a good theoretical explanation for this, which is where the beautiful mathematics comes in, which is very remarkable too. If you consider this function, u of x and t, and for the moment you think of t as a fixed constant, just think of it as a function of x, then given a function of x, you can regard it as a potential function for the linear differential operator, just in one variable, d by dx squared, plus a constant times u. This is a linear operator in u, now, which is very well studied, of course, in physics, with u as a potential. And now if you let this evolve in time, now let time move, in such a way that u is a solution of the KdV equation, then you get a one-parameter family of linear operators. And the linear operator, in general, has a spectrum. It has eigenvalues, discrete eigenvalues, continuous spectrum. And the remarkable thing is that if u is a solution of the KdV equation, then this operator always evolves such a way that it remains equivalent to itself, and therefore in particular has the same spectrum and the same eigenvalues. That's an interpretation you can easily check by a little bit of algebra that's true. So you find that with this, if u is satisfied the KdV equation, you find these numbers coming out which are the eigenvalues of this operator. And these eigenvalues are essentially the constants, the velocities associated with the soliton. So the solitons which emerge, they're hidden, and you can find them by, if you like, solving the eigenvalue problem of this operator. It's a beautiful connection between linear theory and nonlinear theory. And I told you, linear theory is very well understood. We have an elaborate theory, particularly we have the spectral theorem. And now we find a way to connect this linear theory, surprisingly, with the nonlinear equation. So you now have to plug in all the standard linear theory, and therefore you can get very good results about the nonlinear theory. So this in particular enables you to solve the equations explicitly. So you have an extensive theory of linear operators. In particular, you use what's called scattering theory. This leads to general methods for solving these equations. And this is sometimes called a nonlinear Fourier transform. The Fourier transform traditionally applies to linear equations. But here you have a way of going from a nonlinear equation to something which is essentially linearized, and therefore you can, and then come back again. So it's called nonlinear Fourier transform. And it's a remarkable theory which leads to explicit and general solutions, and it's a fantastic bit of mathematics. Now, these equations have the eigenvalues, which in principle are an infinite number, and they give rise to what are called conserved quantities. They are things which are constants, which are unchanged as it evolves in time. Now, in physics, one knows that constants which are unchanged for associated with a system are what are called conserved quantities. For example, things like energy, momentum, in traditional physics. And when you have an infinite number of conserved quantities, that's very remarkable. And in the theory of Hamiltonian systems, which applies, that means that the theory is integral. So these are what are called examples of integral Hamiltonian systems. Very, very special class. Very remarkable class. And when you have conservation laws, they usually, to a physicist, indicate there's some symmetry. So conservation of momentum corresponds to the fact that the laws of physics are invariant under translation in space, and the conservation of angular momentum corresponds to the fact that laws of physics are invariant under rotation in space. So when you have a large number of conserved quantities, you begin to suspect there are a lot of symmetries of the problem. The symmetries are not present, obviously, in the form of the equations. They're what are called hidden symmetries. Somehow they're inside. And it turns out there is a hidden symmetry in these problems, which actually corresponds to a certain group, just the 2 by 2 matrix group, determinant 1. So there's a very definite connection between the theory of groups and the theory of these equations. Now you can, once you've understood that, you can generalize more equations which can be associated with other groups, and you can make more and more lists. The theory can be generalized in all sorts of directions. I mentioned just here 2 more equations that are solved by the same methods, not by taking other groups, but by taking the same group and doing something slightly different to the algebra. One is the Sine-Gordon equation, which is concerned with propagation of light signals in optic fibers. And, sorry, that's the nonlinear Schrödinger equation, and this is called the Sine-Gordon equation. So these are just 2 other ones which form part of this theory of equations that have soliton solutions. Now that's a very quick summary of the work that has been going on for 50 years, but it's a very beautiful theory which has important practical applications and a very elegant mathematical story. But I really want to talk now about the things in 3 dimensions. And in 3 dimensions, the problem begins, from a physics point of view, with what are called Dirac magnetic monopoles. In ordinary electromagnetism, you know, we can have an idea of an electric source, electrically charged particle. And electricity and magnetism appear in Maxwell's equations on essentially equal footing. So theoretically, you can imagine an isolated point source of magnetism, which would then be a magnetic monopole. In the physical world, we don't find these, we find dipoles, but theoretically, magnetic monopole might exist. So Dirac investigated the theoretical consequences of what would happen if you studied the physics in the region of a magnetic monopole. Now, the magnetic monopole, from the point of view of mathematics, is a solution of Maxwell's equations, which are linear equations, and it's a static solution. We're not considering dynamics here, but it is a singular solution. The origin is a singularity. The source of magnet is a point singularity. And why Dirac studied this, he got from this remarkable physical consequences, which led him to explain what's called the quantization of electric charge. Why is it that the electric charge of particles in the world always come in integer multiples of the charge of the electron? And he gave an answer to that based on examining the geometry of magnetic monopoles. It's essentially a topological argument, which is nowadays incorporated in much more sophisticated theories. A very profound piece of work by Dirac. Now, in modern theory of physics, people study not only the electromagnetic field, but also the other forces in nature that occur in the structure of matter. And these equations now correspondingly are not linear, but they're not nonlinear. And in this theory, or parts of the theory, it was observed by Tufte and Polyakov, two physicists, in 1970, that there are things that look very much like the Dirac monopole. They're called non-abelian magnetic monopoles because they depend on using a non-abelian group of matrices. And there are more fields involved in the electromagnetic field, but for these purposes, the other fields are small and can be ignored. If you have one of these non-abelian monopoles, what happens is that very far away, you think all you're seeing is the field produced by a Dirac monopole. You get just spherically symmetric magnetic field. But when you come into the region near the source, instead of finding a singular point, you find something smooth, something without singularity. You find some kind of field that gets rather large, but in a complicated way, but everywhere nicely behaved. That is a soliton. It's a sort of, the soliton is the solution of the corresponding equations here, which describe something that is behaves at large distance like a Dirac monopole, but at short distances doesn't have the property of being singular. Now, singularities are bad mathematically, so this was, when people discovered this, they were very enthusiastic about applying soliton ideas to in particle physics. This was the discovery at that time. Now, there is actually, this is this sort of physical model, there is actually a simplified version of this equation that gives rise to the non-abelian monopoles, which I'm going to talk more about, and where you can actually get very precise solutions, just like you can for the one-dimensional problem. And in this model, the situation is the following. The fields that you study, the potential that you study, is like the electromagnetic potential, but has more components. So the potential is what's called a gauge potential. It has 3 entities, A mu, corresponding to the spatial directions, but instead of being a scalar, it's essentially a matrix. It's a 2 by 2 matrix in the Lie algebra of the group SU2. In addition to that, there is another field coming in, called the Higgs field. The Higgs field is named after Peter Higgs, who is, I'm glad to say, a colleague of mine in Edinburgh. And out in CERN, they're trying hard with the next accelerator to find something called the Higgs particle. If they find the Higgs particle, Peter Higgs will be very pleased. But it takes a long time to build these machines. He's getting older, so it's getting touch and go whether they will find it in time. I hope they succeed. Anyway, the Higgs field plays an important role in present-day theoretical physics. So in this situation is you have two things. You have a gauge potential and you have a Higgs field phi, which is, has no indices, but it again takes values in the matrices. And these things are functions of position, functions of space. So you have these collection of mathematical objects, and then you have a differential equation which describes how they're related. And this differential equation is the following. It's called the Bogomolny equation, and it's actually a very simple equation, and it has very simple geometrical meaning. The equation has the following meaning. You take this Higgs field phi, and you take its sort of derivative, like the gradient of a function, but you take the covariant derivative with respect to the potential A. That's to say you write d of A is the ordinary d plus the bracket of the matrix A with that. And then the curvature, or is the field associated to the potential A, is the antisymmetric tensor given by the bracket or commutator of d mu and d nu, differentiating in different directions. In geometry, differentiating in different directions is what explains the curvature in the middle. And the star here is the duality operator that in 3 dimensions associates something with one index, it gives you something with 2 indices, skew symmetrically corresponding to the orthogonal direction. So this equation here is a very simple equation. It says that this thing here, which has 1 index, is the dual of that one which has 2 indices. And it's an intrinsic equation. You don't need to have indices. It has a geometrical meaning. And it's a very nice equation. And that's the equation you want to solve for these monopoles. Again, you have to put in boundary conditions. And the boundary conditions you require are that this field phi has its length, its natural length in the Lie algebra should go to a constant, say 1, as you go to infinity. That the field f, which I didn't put down, should go to 0, it should decay. And this function phi, when you go to infinity, it has its norm is 1. It takes values in 3-dimensional space. So eventually, its value lies on the unit sphere in the 3-dimensional space, which is of dimension 2. And is defined for every direction as you go along the radial direction in 3-dimensional space on the large sphere in 3-dimensional space. So it associates to a point in this 2-dimensional sphere, a point in that 2-dimensional sphere, and that has then a topological degree, the number of times the first sphere covers the second sphere. If you take circles, you think of how many times a circle winds around another circle. This is the 2-dimensional analog. This is an example of a topological invariant. And this is a certain integer k, which can be positive, negative, or 0. And in the physical interpretation, this is identified with the magnetic charge of the soliton. So the basic case is k equals 1. That would be magnetic monopole charge 1, unit charge. If you had minus 1, it would be the opposite negative charge. And if k is greater than 1, you're thinking something which is like several single monopoles brought close together, interacting in some way. So this will be a single soliton, this will be kind of multiple soliton. And all of these are then determined by the topology, which requires that this number k is an integer. These equations can actually be solved fairly explicitly. You get a lot of information about them, and you find that the solutions are not unique. If k is bigger than 1, they have a number of parameters, degrees of freedom. The degrees of freedom form a space called the moduli space. It's not just a linear space, it's complicated topology, but it has dimension 4k. And you understand that saying that each single monopole has 3 degrees of freedom for the position where it's located in, say, dimensional space, and has 1 extra degree of freedom to do with what's called a phase, a certain angular variable. And therefore each monopole comes with 4 degrees of freedom. If you have k of them, you get 4 degrees. So that 4k degrees. So this is approximately how you understand these degrees of freedom. Now, so that's a very quick summary of what you know about these equations. So they are solitons arising in the theory of monopoles of this form, and they are fully 3-dimensional, and they have an important relation with topology, and you can solve them very beautifully by some very beautiful mathematics, which I'll come back to later. That's 3-dimensional example. Let me now mention a 4-dimensional example. In 4 dimensions, then these are the solutions of the equation we're talking about now are what physicists call instantons. Instantons because so to speak, 4 dimensions is like space-time, and a point in 4-dimensional space-time is what you call an instant. So, instanton. And the equations that govern them are called the Yang-Mills equations, after the physicists who brought them in. And the equations look very similar to what we had before. Again, you have a gauge of potential A for SU2, but now defined in 4 dimensions instead of 3. And now you can form the curvature of this field, which has 2 indices. But now in 4 dimensions, 2 is dual to 2. You have 2 directions here and 2 orthogonal directions. And therefore, this dualizing operator can transform F into something similar. In particular, you can require that it should transform it into itself. Then that's called the self-dual Yang-Mills equation. That's a very simple, it's a first-order system of equations, differential operators. And these self-dual solutions are what are called instantons. Again, you have to put in boundary conditions that the curvature should decay at infinity or in all directions. And again, there is a topological invariant decay, which is not quite so simple to describe at this time, but believe you did. And then the solution of these things are again localized in space approximately. They fall away, and they have parameters which correspond to imagining k equals 1 is the basic one, and for k bigger than 1 you have a number which come together. They can be very far apart where they look like far separated bumps, but as they come together they interact some way, and you get a 4-dimensional picture generalizing the picture I gave you before for water in a canal. So they have the same general features of localization plus interaction. And the number of parameters here is 8 because a single instanton has a position, and this time it has 3 angular variables for phase. So this whole theory can be developed mathematically. There's a very beautiful way of solving them. And all I'm going to say is the following. There's an explicit construction of this solution of these equations using what's called the Penrose-Twister theory. Roger Penrose is another colleague of mine in Oxford. Now, sorry, I'm now in Edinburgh, but when I was in Oxford, he was my colleague then. And this is a very beautiful way of transforming these equations into using complex analysis into complex algebraic geometry. And then you use methods of complex algebraic geometry, and you can solve these equations in a miraculous way. And this is, in some sense, again, some kind of nonlinear Fourier transform that transforms the nonlinear equations in something involving essentially linear information in complex variable theory in a different space. The twistor space is not the space you start with, it's like another space. Anyway, this is a very beautiful bit of mathematics, which I won't say more about just yet, and it leads to explicit solutions for these instanton equations. Now, you remember that I told you that the KdV equation could be solved because there was this beautiful connection with the linear operator in which the function u, which is the height of the water wave, is taken as the potential for a linear operator. Now, this theory here, much more complicated equation I'm talking about, also turns out to have a linear operator associated to it, which plays a similar role. But unlike the previous case of the KdV equation, this other operator does not have to be invented produced out of a hat. It's not something extraneous. It's part of the physics. In fact, it's what's called the Dirac operator, introduced by Dirac. So in physics, there is a thing called the Dirac operator associated with these systems, and the Dirac operator is the linear operator, whose study leads you to understand the nonlinear equations which we've been talking about. So again, the relation between a linear equation and nonlinear equation, but now involving higher dimensions, involving 4 dimensions instead of just 2. So this is somehow the same story, but in a much more beautiful way. Now, a little digression here. These instantons I'm talking about are in 4-dimensional space. But you can, mathematically, forgetting about the physics, talk about instantons on curved manifolds. All you need to define the equations is a Riemannian metric. Then you can define locally the notion of orthogonality, which it comes into the star operator. And then the equation makes sense geometrically on any 4-dimensional manifold. And these, of course, you can't solve them explicitly now because the 4-dimensional manifold may be very unknown. But you can study the general theory. And again, there are solutions which are localized. The local story is very similar. But the global story is complicated. And that will reflect, in particular, the global geometry of the 4-dimensional manifold. And these were used by Donaldson, Simon Donaldson, who was one of my students at the time, in a spectacular way to derive entirely new results about 4-dimensional geometry, which are totally unexpected. And these results in 4-dimensional geometry are probably one of the most spectacular achievements in mathematics of the last part of the 20th century. They were totally unexpected, opened up in a big new field, and they came from physics in this way, but applied by him in a really remarkable geometrical way. This was a very big achievement, but I put it in brackets because I'm not going to talk more about it. Now, let me go back to the four-dimensional space. We have four-dimensional space. We have these equations in four-dimensional space, these self-dual Yang-Mills equations, which gives rise to these instantons. We can, if we want, ignore one of the coordinates. Look at functions, everything which are invariant under translation in, let's say, the fourth variable. Then automatically we will get an equation in 3 dimensions. Example of this dimensional reduction process I mentioned before. And if you do that, then the Penrose-Twistor theory, which works well here, will give rise to a similar theory in the lower dimensions. Now, the self-dual Yang-Mills equations, when you reduce them, become exactly these Broglie-Molyneux equations I mentioned earlier. In other words, the 2 higher dimensional examples I've talked about, one is concerned with magnetic monopoles, the other is concerned with instantons. They're essentially the same equation, or this one is got by reducing this one dimension. And the same methods which you can apply on one side, apply on the other. So both of them are really examples of the same equation being studied by the same methods, but in slightly different conditions. Now, if you go from 4 to 3, that's one reduction, but you can go from 4 to 2. 4 to 2 dimensions, you ignore now 2 variables. And again, now we will have a different interpretation of our variables. We may want to have our variables thought of one space and one time. If you do that, then you should change the signature of the 4-dimensional space from positive definite signature to Lorentzian signature, or even two signatures. But this can all be done in a formal level. So you can get from the 4-dimensional equation, by 2-dimensional reduction, lots of equations involving space and time. And I mentioned before at the beginning, this way you can get essentially all the known solid equations of this type, the KdV equation, Sine-Gordon equation, nonlinear Schrödinger equation, and so on. All of them can be obtained by systematically reducing this one equation, but in different ways. Now, this equation is said to be one master equation. Once you specify the Lie group, in this particular case, these all come from the just 2x2 matrix group, then this equation is determined, nothing else, no other ingredients. But to make the dimensional reduction, you have some choice. First of all, you have to decide which variables to drop out. And so you reduce from 4 to 2, but there are different variables. In the 4-dimensional space, you can drop out. For example, if you, in Lorentz space, you have the difference between light rays and spatial directions, and they give rise to different sorts of equations. So the choice of direction is important. Secondly, these equations are geometrical. They don't depend on any coordinate system. Or, if you like, from a physicist's point of view, there's a gauge freedom, which is how you choose the potential to represent the function. And when you want to write a differential equation down, you more or less have to choose coordinates. You've got to choose a particular gauge, as they say. And the choice of one gauge will give rise to one equation, or choice of another equation will give rise to another equation. See, differential equations are things that you write down in algebraic form. But if you make a change of variable, you'll get a different looking equation. And it's not easy to see in advance which equation is equivalent to which one under change of coordinates. So the choice of coordinates comes in here, because this one works for all coordinates, and then you get different answers depending on which coordinates you use. So this is the way in which the 4-dimensional theory leads to a 2-dimensional theory. And as I mentioned before, the Dirac operator is the linear operator here. That gives rise to these linear operators that you use to solve the 2-dimensional problem. And the Twistor theory, which I mentioned, comes down here to what's called the inverse scattering method, the technique which is used in the theory of these nonlinear equations, which is classical linear operator theory, and is called the scattering theory and the inverse scattering theory. This whole subject here, by the way, is due, a lot of it, to Richard Ward, one of Roger Penrose's students, and there's a book by Mason and Woodhouse which explains the whole process of going from 4 dimensions down to 2, how you make this link. And I recommend this to anybody who's interested as a way to understand this whole connection. Now, I want now to come to the last topic I want to talk about, because this represents a different sort of phenomenon. Forget about the details. What I've been talking about rather rapidly is a lot of beautiful mathematics where you can solve explicitly some particular equations which are interesting, have different physical interpretations, by a marvelous process of associating a linear equation to a nonlinear equation. That's all you need to remember. There's a technique, it works beautifully, and in some sense all part of a single theory. Very interesting. But, of course, limited to certain classes of equations. If I give you another equation, none of this works. So, is that all you can do? Well, here is another problem, which is somehow not the same, but we can get information about it. And I want to therefore explain to you because it's a new kind of approach in a way. This deals with another problem in physics, which are to do with particles called skyrmions. Now, skyrmions, as the title indicates, are some kind of soliton. The word on on the end, you know, you have protons, electrons, so on. Everything which looks like a particle has an on the end. If you're a physicist and you want to become famous, the important thing is to have a name which lends itself to adding on. See, we have Fermi, we have fermions, there are Bose had bosons, but, you know, some names don't lend themselves. My name is no use for, to a particle. I never become famous that way. Skyrm had a good name. So skyrmions stuck. Just think about your name when you... Now, what Skyrm was trying to do, and this is really very far in advance of his time, this is 1961, even before this theory of solitons got going. But he was trying to develop a classical model of the nucleus, not a quantum mechanical model, just a classical one. One knows that equations have to be nonlinear. I mean, that's what makes matter stick together. It doesn't diffuse. So somehow nonlinearity has to be important. Also, he wanted something to give you a particle number. Now, what is the number of protons in the nucleus? An integer. And so he decided that this should come from topology. This is really far ahead of his time. And so what he did was to say, let us consider the following kind of functions, fields. They are defined in three-dimensional space. So this model, for the moment, is no time. You can study time evolution later. Just static models. Function of three-dimensional space, and it takes its values in the 2x2 matrix group, SU2, which is actually the same as a three-dimensional sphere. Unitary group, determinant 1. So you take a function who's a three-dimensional space, depending on three coordinates, lying in this group, which is really a three-sphere. And you put a boundary condition, as you'd expect, that as you go to infinity, in any direction in three-dimensional space, this function should go to a fixed point on the sphere, the point 1 in the group, the unit matrix. Now, if you do that, then you see you can think of this map G being extended to infinity in space by just adding the one value, 1. And if you add a 1 point at infinity to three-dimensional space, you get the three-dimensional sphere. Like you add a point to the plane, you get the two-sphere. Or you add a point to a line and you get a circle. So this gives you a continuous map from the three-dimensional sphere to the three-dimensional sphere. And just like we had in the case before of monopoles, where the sphere had dimension 2, this has a degree. This degree, the number of times this sphere covers that sphere, is an integer, positive, negative, or 0. And so Skyrm interpreted that integer as the number of protons or neutrons. In this theory, you ignore the difference between protons and neutrons, they're nearly the same. One has electric charge and the other one does not, but forget it. The theory is the theory of protons and neutrons and how many there are in the nucleus. So that number k describes the number of protons. So this is the his kind of field. Of course, you have to have some equations which this has to satisfy, or if you prefer, you have to define the energy of the system. Once you define the energy of the system, then you try and solve the equations which minimize the energy to give you the equilibrium state of the object you're studying. So the energy he wrote down was a very function. Now, what this equation is shorthand, I could write it down in lots of indices, and it would take 2 pages, but shorthand is better. The first term, both of them are integrals over three-dimensional space of some density function. And this first one, dg is the map, don't forget, from the three-dimensional space into this three-sphere, and you take its derivative. Well, the derivative is, of course, given by lots of partial derivatives. There are 3 directions here and 3 by there, so it's a 3x3 matrix. And this expression here simply means the norm squared, the sum of the squares of the entries of that 3x3 matrix. Okay, so that's the natural norm, and you integrate that over space. That's a kind of natural kind of gradient squared energy which turned up all over the place in physics. The second one is a bit different, because if you didn't have the second one, then you easily see that one there is very badly behaved. Particularly if you rescale things, then you can show this will expand, this will change, and things will behave badly. So you have to compensate by adding another term, and the other term looks complicated, but it's very similar. What you do, you take this 3x3 matrix, and you replace it by what's called the 2x2 minus of that 3x3 matrix. So you have another 3x3 matrix. Now you take the squares of the entries there. Now, that operation is really dual to the first one, and this bit here confirms length, really. The derivative tells you how things expand linearly. This one controls area, and in 3 dimensions, area and length are dual. So these have sort of dual aspects, and in fact, if you rescale under just changing the scale length in R3, one of them gets bigger and the other gets smaller. And because one gets bigger and the other gets smaller, they can balance out and produce a stable solution. Otherwise, the solution will either go off to infinity or it will collapse to a point. So these 2 parts are essential, that you have the 2 together. And then given this energy function, you try and solve the equations with given number k, you try to minimize this function. And the standard way in the calculus of variations leads you to the differential equation, so-called Euler-Lagrange equation, which you write down. I'm not going to write it down, it's a routine exercise to do that, and you get the equation that will define the skyrmion. And the question is now, solve that equation. It's a complicated nonlinear equation in 3 dimensions, with certain boundary conditions. It's a well-defined problem. Now, it's very difficult, this problem. First of all, it's not one which we can solve at all by any method. Nobody has any explicit analytical solution. Even for the case of k equals 1, which will describe a single proton, there is no analytical solution known. And all you can do is to use numerical methods. Now, numerical methods with computers are fine sometimes. But in a very complicated problem involving many degrees of freedom and a lot of nonlinearity, that's not enough. You can't just charge in and give your computer a lot of calculations to do. You can go down the wrong track and you get the wrong answers. So numerical calculation alone is not enough. You need to have some better ideas. Now, let me say this again. For k equals 1, a single particle, again you try to do the obvious thing and try to look for a spherically symmetric solution, hope that the solution you're looking for will be spherically symmetric. It seems reasonable with 1 particle. And in fact, when you require spherical symmetry, then you cut down the number of degrees of freedom and you reduce to an ordinary differential equation instead of partial differential equation. Then you can apply numerical methods much more straightforwardly, and you can find at least a numerical solution, and that seems to be accepted as the solution you need for a single proton. So if you like, the nucleus of the hydrogen atom is given by this skyrmion, the basic skyrmion, and Skyrm did that. But then what happens if k bigger than 1? Now here it's very difficult. As I say, even numerically, it's very hard to find how to go about it, what the answer should be. For example, k equals 4, with the nucleus of helium, we'd like to know what it looks like, and these methods it's very hard to make any progress. So what can you do? Well, here is where you start to have a combination of, mathematics is not all about proving theorems and doing things by rigorous step-by-step argument. Sometimes you need flashes of inspiration. You need guesswork. You need intuition. You need sort of real insight from somewhere else. And so this is a story about that sort of story, insight. So the question you can ask is, we have these other equations, these ones that gave us instantons and monopoles, which we can solve explicitly. And they are equations in 3 and 4 dimensions, which are coming from physics. They describe different things. This describes monopoles. They're not describing protons and neutrons, but maybe, if you're lucky, perhaps they behave somehow similarly. Well, that's a reasonable guess, and you try and follow that through. Now, the first thing is, can you get that? How would you relate skyrmions and instantons, for example? Well, there's a very simple way you can go from one to the other. If you've got one of these gauge potentials, which is 4 dimensions, what you can do is to take 3-dimensional space and the 4th variable, and now we're not take solutions which are independent of the 4th variable, which is what we did to get monopoles. What you do is you do what's called parallel transport in this direction, the 4th direction. That means you solve an ordinary differential equation given by the covariant derivative equal to 0 in this direction, and that means you get an element in the group. The parallel transport starts off with the identity element and moves it somewhere else. And if you do that for each point in space, then you will find yourself a map from space into the group. So it's a very simple operation to carry out. If the group was abelian, you could write it down. In non-abelian case, solving this parallel transport equation is solving an ordinary differential equation. You can't actually write it down, but it's unambiguously defined. And again, you can easily check that if the first field up 4 dimensions satisfy the conditions at infinity, everything decaying, then the one you get down below will also satisfy the right conditions to be a Skyrm field. So this way you can convert these fields, which are Yang-Mills fields, into Skyrm fields. Now, and moreover, you can easily check that the topology is fixed together, that the instanton number, integer there, corresponds to the Skyrm number in the other problem. Now, not only is it true that the integers correspond, but even true that the function spaces have the same homotopy type. This first problem is a problem defined as an infinite dimensional function space, which consists of all gauge transformation, all gauge fields up to gauge equivalence. And that has a certain topology. The space of all maps from the three-dimensional sphere to the three-dimensional sphere is a complicated n-dimensional space. It turned out this map we construct takes one into the other in such a way as to preserve all their interesting topological properties. In particular, the components of the space is just the degree, but much more than that is true. So these spaces are topologically essentially the same. That's the first observation. So that's a good hunch that perhaps the two problems are connected in some way. They're both defined on essentially the same topologies. Now, it's also known that if you're inside the space of all gauge fields for the four-dimensional problem, you look at those that satisfy the instanton equation. I told you that form the moduli space mk of dimension 8k, that's finite dimensional subspace of an infinite dimensional space. Now, because so much is known about this problem, we know that if you increase k, then eventually this space gets closer and closer to capturing all the topology of the function space. So inside this big function space, the function space is more or less independent of k. As you increase k, you get bigger and bigger levels of the space, and somehow they capture all the holes in the space. That's the thing you can prove mathematically. So we know that if we therefore do the following, well, let me put it this way around in words, this space mk is a good finite dimensional approximation to the whole function space. It's finite dimensional, but if k is large, it's 8k dimensional, and it topologically captures a large amount of the space. So that's what you might call a good truncation of the space. Let me go back a moment. If you were dealing with problems in analysis, you have an infinite dimensional space which is not linear, then one first thing you can do is try to cut that infinite dimensions down to finite dimensions. Then you can use standard methods of numerical calculation. You can take a discrete approximation, put it on a computer, but how do you approximate infinite dimensional degrees of freedom? That's very hard. So the first thing you do is you try to find a finite dimensional approximation. In linear problems, people do that standard way. You take a Fourier series and cut it off after finding many terms. But in nonlinear things, how do you know what a cutoff is? How do you know what to throw away? And the point is the topology of the space may hide a lot of important information, so you want to reflect that topology in your cutoff. That's sort of the intuitive idea. But this space does reflect the topology, so okay, that's a good hunch. So we try that. So then you try this finite dimensional space, and now you move it over by this operation, moving from the Yang-Mills fields into the Skyrm fields, and you find yourself a finite dimensional approximation to the space of all Skyrm fields, which we know has the same topology, so it ought to be a good truncation. So building one hope on another one, we guess, we make conjectures, speculate. We just try and say, perhaps this is a good finite dimensional approximation to try and solve the equations. Now we can use numerical methods. We have this finite dimensional approximation. We apply numerical methods in finite dimensions, which is much simpler, of course, than infinite dimensions. You've got away with infinities. And what happens? Well, remarkably, we get good results. I mean, this is, showing that all this intuition, this guesswork, somehow worked. I mean, I can make all these marvelous conjectures and say, well, the topology should be a guide. We should do this, we should do that. But if I don't get any calculations in agreement with the results, I was wrong. But the numerical calculations confirm that you get good answers. The answers seem to be the best possible insofar as you can check them. So this really is a rather remarkable process by which we've approximated an equation which we compared an equation which we can solve to one which we couldn't solve. And that comparison is done because the underlying topologies look the same. We've guessed that was a good comparison, even though the equations are very different, even though the physics meaning is very different. And we found out of that a guide which seems to lead us to find the right kind of solution. Now, as we say in Britain, the proof of the pudding is in the eating. I don't know what you say here in Brazil, but I'm sure you eat similar things. If it tastes good, it works. So this works at the numerical level. You got there by a succession of physical intuition, physical intuition because you're talking about particles, they should be the same way, mathematical intuition because we think the topology should be a guide, and so on and so forth. All of these are bits of guesswork. If they work, you say it's inspired guesswork. If it doesn't work, you throw it away and try again. So this time it turns out that the guesswork works. So let me try and conclude, and I'll give you a few pictures just at the end to illustrate this. So soliton theory has many important physical applications. It has some beautiful mathematics involving D groups, algebraic geometry, and topology. And it provides a crucial insight into a special class of nonlinear differential equations. This covers both 4 dimensions, 3 dimensions, 2 dimensions. And so in some sense, if we go back to my beginning, linear mathematics is very much under control. Things which are close to linear are also under good control by approximation. But things that are nonlinear are in the unexplored ocean. So I think of these solitons as like islands in a large ocean of unexplored nonlinear problems. We don't know what is out there. We have very little clue. The main shore we start from is the linear theory. We can explore out by boats near there. But if you find an island, way out in the middle of the Atlantic, you move your base there, and you can explore around that island, and you know a lot more about the ocean. So that's the way you should think of the soliton theory. It applies to special classes of equations, but the equations are not as unusual, not as rare as you think, and maybe you can approximate those other ones that you can understand or get insights into them. So it's an insight into the nonlinear world which we exploit as best we can. That's sort of how I'm trying to summarize the process. And in a way, because it involves both differential equations, geometry, topology, and analysis, lots of different physical models, various kinds, it's an ideal common ground for mathematicians and physicists to work together. And I collaborate on these things mainly with physicists of various kinds, and the other mathematicians who collaborate with other physicists. It's a very fruitful area for interaction, and you can take your pick what you want to work on. You can work on the one-dimensional theory in great detail. You can work on the approximations to get more physical results. You can work on the higher dimensional models to get results like particle physics. And you can work on skyrmions if you want to go closer to nuclear physics. So you've got a choice very much of where you want to work. Now here are a few references. These are chosen at random in some sense because the literature on this is vast. The paper of Peter Lax is early one, is one of the way explains how the linear operator comes in to help you solve the KdV equation. It's a very beautiful paper, very clear, and I recommend it to anybody who wants to look at the things. This paper is an excellent starting point. Then if you want, let me just jump down here, down the bottom, there is a book here by these 4 authors, which is a rather extensive book describing a number of different nonlinear equations which are important in physics, the one-dimensional ones, and how you solve their solitons. It's an extensive theory covering a lot of examples with a lot of physical application, and these are really applied mathematicians or physicists. Then the one in red here is a book which is a collection of articles from scientific journals which is about the solitons which appear in connection with particle physics and their role in physical theory. I've already mentioned the book of Mason and Woodhouse. Here are the details about it, which explains how to get from the 4-dimensional integral theory to the 2-dimensional ones. And then there's this very new book by Manton and Sutcliffe, Topological Solitons, published last year, which is a very extensive survey of the topological solitons I've been talking about, the monopoles, the skyrmions, all the theory of those, their physical interpretation, and the numerical results, and the pictures of what you get, and so on. So this is a description, really, of the second half of my talk. So this gives you just a brief indication of the wide range of literature there is from different points of view by different people with different purposes. So let me finish just by giving you some pictures, because equations are one thing, but nothing like looking at a picture. And here is a picture, which I'll explain in a moment. This picture is meant to describe the following thing. This could describe either, all the pictures I'll tell you about, could either be thought of as pictures of monopoles, or they can be thought of as pictures of skyrmions, because it turns out that they're so similar, the pictures are the same. So the idea is you have 2 monopoles, let's say. They're originally far apart, and so I represent them by spherical blobs. It doesn't mean it's all there, but if you draw the energy function, it tails away rapidly away from here. So most of the energy is in this lump, and it's very small elsewhere. So approximately you think of it as localized in that ball. So you have these two monopoles which come in a head-on collision. Now the very first question you ask, when they interact, so what does it look like at the moment of interaction? Well, your first guess might be that it forms something spherically symmetric twice as big. Turns out that's not true. There is a solution which is spherically symmetric, twice as big, but that's not a stable solution. It decays. And what you find is that the solution you get is actually a toroidal shape. It's colored in a ring. So the two things come together. As they approach, they bend. If you think of these things as being some kind of jelly, they bend round. And at the moment of interaction, they join together and form a single ring. And then you can ask, well, what happens after they've collided? How do they come out? The answer is they don't come out in the same direction as they went in. They come out at right angles. And what happens is this ring, now having been formed one way, breaks off in the other way. So the fact that we understand what happens at the moment of collision gives us a good guide as to what happens under the collision process. So it's the opposite way around. Before I said you have solitons interacting, they make a mess in the middle, forget it, and then you see what happens afterwards. Well, here it's the other way around. They don't make a mess in the middle, they make a rather beautiful picture in the middle. That gives us a guide as to what's happening later on. But basically this is the two things coming in, two things going out, and a picture of what happens at the point of exact collision. There's a nice movie I got made some years back from IBM, which shows you what happens if these collide not in a direct collision, but slightly displaced from one another. Many more interesting things happen, and you can get pictures showing what they do on a nice video. Well, that's the simple case of 2. But I want to give you some pictures of 3 and more. And here we get into a surprise, because if you have let's say three spherical blobs, they could be monopoles, they could be skirmiones. And imagine when you have 3, they're arranged symmetrically to start with, very far away, forming the vertices of an equilateral triangle. When you have 2, there's not much choice. They are symmetrical about the midpoint. With 3, they could form other figures, but let's take the nice case when they form an equilateral triangle. Then give them a bit of a push. They come together. And the point when all get into the middle, what happens? Well, some complicated picture, what is it going to look like? Well, I can take a guess here. Will they form a sphere twice the size of a torus? Or what's going to happen? Well, you wouldn't guess, really. I think I'd give a prize, a bottle of champagne to anybody tell me they could guess this. But I have to have it in advance, mind you. You can't say I knew it all along. And what you get is, well, I'll just show you one at a time, so not to give you the hint away. You get this picture here. In other words, this is meant to be, the energy density of this object in the middle is concentrated along the yellow part with a tail fall off elsewhere. So you recognize this immediately as some smoothed out version of a regular tetrahedron. And now if I told you that was something representing 4 particles, you'd have said yes, of course. But it's representing 3 particles. So the 3 particles, when they collide, look somehow like 4. They've got extra symmetry that you wouldn't expect. It's rather remarkable. And you can follow through with the collision process and find what happens as the tetrahedron forms one way and breaks apart another way. So identifying these solutions is very interesting, and this is, they have some nice symmetry properties, and again, this is true both for the monopoles and for the skyrmions. So this is the one, the nucleus with 3 protons, if you like, from this point of view. What about other numbers? Well, here is another picture. This is what you get if you have 4 particles coming together. And when 4 particles come together, lo and behold, you get a thing looking like a cube. It's concentrated around the edges with holes in the middle. The holes in the middle are where the energy density is very low, and the corners are where the energy density is very high. Here's another one. This, I think, is what you get when you have 7 monopoles coming together. Then they form nice dodecahedron. Well, they're all rather beautiful pictures, aren't they? Now, you might say, well, what happens? It happens that the tetrahedron and the cube and the octahedron and their duals exhaust all the regular solids. So you might say, well, what did God do when he wanted to make something with different numbers of particles, different numbers of protons? Well, he had a solution, he just didn't tell us, and they look like this. So what you get are things that look, pretty regular, but they're of course not perfectly regular. There are no perfectly regular ones with the other numbers, but they're as regular as you might get. And this is this is energy density picture, and here is a schematic picture, the kind you find in chemistry labs in the old days. When I was at school, you build these things with, particles and valency bonds and so on, which indicates schematically the combinatorial structure of which this is meant to be some kind of smoothing. And you can see very nice polygonal shapes appearing there, and I can give you another one. the numbers go on. These are all done numerically after you know exactly what to look for, with a bit of help from the exact solution that we know about, and using numerical calculations. You can do quite a lot, and so all the way up to 22, and you find these things persists. There we are. So it's great fun. I mean, I don't do the calculations. I have friends who do these calculations, but they're very skillful. But it's this combination of mathematics, physics, some computing skills, and, you know, the way they all fit together that I find so attractive about this subject. Well, I'm sorry I've gone on a bit long, but I didn't start on time, you know. I had this delay. And I hope I've given you some indication of the excitement of this field, where you have lots of an area between mathematics and physics, between different parts of mathematics, and also involving computers, which is still going on. It's had a long history, going back 30, 40 years, but things are still happening at the moment, and there's plenty more work for the younger people here to take part in. Thank you.
Well, thank you very much. It's a very exciting lecture. I think you've really obtained your goal to excite all of us and show all your talent in blending all this mathematics and intuition together. Please, any comments or questions?
I have a small question about the case of skyrmions.
Yeah.
When you showed us there was this particular solution,
Yeah.
which was obtained by symmetry, by spherical symmetry, and based on the intuition I have on one-dimensional solitons, KDV, and so on and so forth, I was wondering if there is a way of using such solutions, symmetric ones, to generate higher-order solutions, more complicated ones, like the ones you get, like Darboux-Backlund transformations from the original ones in the KDV case, and perhaps that's a way of trying to go into the n-dimensional solutions of the skyrmion equations without having to use approximate solutions.
Well, so the question is in the one-dimensional theory, which is referred to, the method of solving these equations, which corresponds to this nonlinear Fourier transform I mentioned, because it linearizes them, there's a way in which you can somehow add solutions and get new solutions. You can't add them naively because the equation is not linear. But there's a clever way in which you can add them, which have a long history. And so this technique is used by many people to generate solutions, more solutions out of old ones. The question was asking whether similar things might work with these three-dimensional equations. Now, the skyrmion equation has no good properties at all, so unlike the monopole equations, has good properties, and there the same techniques work for explicitly solving it, and the methods of generating more solutions out of old ones will have a counterpart in those equations, but because it's higher dimensional, it's not so straightforward, and the skyrmion equations don't have any good properties at all. So, I mean, I'm not saying it wouldn't be possible. Maybe it's worth thinking about, because the equations seem to have so similar, and you might be able to use that similarity to make more guesses. But of course, you see, the solutions we get for the skyrmion tend to look very symmetrical, all of them. And of course, you might say that any symmetrical thing made out of 6 bits is made out of two smaller symmetrical bits, or smaller bits cleverly put together. And in some sense, that might be true. But whether you could have guessed the particular form of symmetry in advance, I doubt. I think it's possible, but I think it's more that these way of adding solutions is part of the general theory. That theory transposes to higher dimensions, but because of higher dimensions, it's slightly more complicated. But it is an interesting question. Maybe there are cleverer ways of doing it. You know, we made one guess which worked nicely. Maybe you have a better guess. We're better.
More questions or comments?
First, a comment, which is, it's very nice to hear you speaking and promoting numerical methods as a way of getting inspiration and doing better and beautiful mathematics. that's fantastic. Maybe I owe you a bottle of champagne for that.
Thank you. I'll hold that.
So, and the other thing is regarding numerical methods, and you're mentioning about, putting in a lot of information, from what I understood, into numerics. How sophisticated and is the method enabled to capture all this? Say, I'm thinking along the lines one uses these days. There's a lot of talking about, say, geometrical integrators, symplectic methods for Hamiltonian systems, and so on.
Well, I mean, the numerical techniques are done by, not by me, my sort of younger people. They apply a variety of numerical methods. They apply simulated annealing as a technique too, because these are problems where there's a large number of local minima, and you have to get the absolute minimum. And so you have to give yourself some thermal noise to jump around. And so they do that a lot. And what they do is they start with different initial conditions, do them many times, confirm that when they got the absolute minimum, it always gets the same answer. So they use that, but it was before this connection between skyrmions and monopoles was discovered. Even for the case of charge 2, people got the wrong answer. They were looking for spherically symmetric things. They had no idea they should be looking for a torus. So unless you know roughly what it is you're looking for, you go down the wrong path. You apply numerical calculations in the standard way, and you don't get anything sensible. Now, maybe there are more sophisticated methods that you refer to. Maybe applying those would be, but all I can say is they weren't done. For people who worked in these things, there were a lot of physicists who worked with big computers, and they got wrong answers. Because the methods that they used certainly didn't give them any correct insight. So what we got here was a new insight which led in certain directions, which tell you how you should start your approximations and give more information. I didn't give all the details here. You get rather precise information. These symmetrical solutions are one, but even without symmetry, you can get rather precise ansatz for constructing solutions which depend on ordinary differential equations. So you do a variety of methods, and different ansatzes, different insights, and then numerics. You can compare those with brute force numerics for small values afterwards as a test. And so the people who do this are testing it out, because you do numerical calculations, you're never sure you're right. How do you know that the answer is correct? You can't prove it. You try and try again. If you can't improve on it, you think it's correct. At the end of the day, it's a matter of art and skill, how good you are as a numerical calculator, as to whether your insight, you think you've got it right. These chaps, I think, are pretty good, certainly by various methods. I believe the answers are correct, but there's no proof for these things.
Thank you.
Other questions?
How do you account for the spin in case of spherical symmetry?
For what?
In your model,
Yes.
how do you, in the skyrmion, how do you account for the spin of the part?
Spin. Well, that's an interesting question. I mean, I think of course, that doesn't become a real question until you start wanting to quantize the problems. But people have looked into the skyrmion and decided, it should be treated as a fermion. I mean, you look into the topology of things a bit, and what happens when you interchange particles. And then with topological arguments, you decide whether it's integral spin or half-integral spin. So this has been looked at geometrically and as a way of justifying what you should do quantum mechanically. Because what happens after you've found the classical solutions that you should try to quantize? And some efforts have been made in that direction. And so the question of looking at the spin has been looked at. And you know what you should be getting from the comparison with the real physics. The question is, can you justify it from the point of view of the equations?
Thank you. I'd like to make one remark about the numerical calculations. The KdV solitons were discovered numerically in 1964 by Martin and Gardner.
Yes.
I saw the long sheets of calculations. I didn't believe it was true at the time.
Yeah, well, I think I mentioned that. I mean, what actually happened, if I understand correctly, was the people working on these equations, they were just, early on, they were just trying to see how complicated interactions could be, so they put the initial conditions in, they put the machine going, they went away to lunch, and they forgot about it. When they came back, they expected to find a big mess, and lo and behold, they found these beautiful, same things coming out the other end. They couldn't, it was just, if they hadn't gone away for lunch, so the advantage, it's a bit like the discovery of X-rays. You make a mistake, and then you suddenly discover something beautiful. But of course, the smart thing is you recognize what you found. Once they saw it, they knew it was important. They did it again and again, more calculations. So they took advantage of the discovery. But it wasn't, accidental discovery. They ran the computer for a long time, forgot it was on. And so, remember, sometimes make some mistakes. Forget about things is a good idea.
Oh.
So we had the microphone. I can't hear you.
fala português?
Eu vou tentar. Em school, estudas, kits, makes, forms, spaces.
Okay.
Did you understand it?
No, no.
No. No, sorry. Você pode perguntar para ele depois. Alguma pergunta? Any more questions? Maybe.
Younger people, there's people in the back row seem to be afraid to ask questions.
Maybe it's time to say that Michael will give another talk, very intriguing, as always, on the nature of space next Thursday at 5:30 at Copeia in the URCA, the old rectorship of the University, Federal University of Rio de Janeiro. So, em português, o Michael Atiyah vai dar outra palestra aqui no Rio de Janeiro, no ambiente da antiga reitoria da Universidade Federal do Rio de Janeiro, na URCA, na Copeia, às 17h30. Well, before I finish, you should look back.
I see, yes, oh, that's right. Yes,
Now, this was the evening at Oslo, with the King of Norway in the middle. The one on the left is a singer, a great friend and co-author of Michael Atiyah. And of course, he looks happier than the three of them. Thank you very much.
Thank you. Thank you. And this picture shows I can dress properly when I want to.
Yeah. I want to say that tomorrow we'll going to know the new winner or winners of the Abel Prize. So you are the king until tomorrow.
I speak too fast, but I tried. I tried.